In the Introduction to Digital Electronics course, we built a 4-bit timer using D flip-flops that were connected sequentially. It was a lot of work, but it showed how we could use electronics to keep track of time by counting the rising edge of a clock signal. Later on, we also saw that there was actually an IC dedicated to being a timer with a single 4-bit counter module inside of it, the 74HC193. The logic symbol for this IC looks like this, with 16 unique pins, including power and ground, and it is the exact logic element that we want to duplicate in this lesson to make our own 4-bit timer module inside of a CPLD. However, let's simplify the logic symbol for our version. We'll get rid of the parallel load enable and data functionality, but we'll keep the master reset and we'll combine the clock up and clock down pins into a single clock that should count up. And now we have a logic symbol for the device that we'll be creating inside of our CPLD. As long as master reset is held at 0 volt or ground, the logic diagram will look like this, and the binary outputs will increment with every rising edge of the clock, just as we saw in the D flip-flop example earlier. To build the Quartus project for our CPLD, we'll start by using the new project wizard. I'll save the project on the desktop in the FPGA/Lesson 6 folder, and the name of the project will be Lesson 6. We're using the EPM 3032 ATC44-10 device, so select that one in Quartus, then click Next, Next, and Finish to make the project complete. Next, we'll add a VHDL file to the project, and now we're ready to write some code. The first thing we need to include is the IEEE libraries. Specifically, we'll be using the standard logic libraries, and this time we're also going to be using the unsigned standard logic library. This library allows us to add standard logic signals together. Now we'll build the entity for Lesson 6. The port definition has 6 pins, a master reset input, a clock input, and 4 LED outputs. I defined the pin connections in comments to avoid confusion later on. Notice that the LED uses something called a standard logic vector. This is actually an array of 4 standard logic outputs, one for each LED. Using standard logic arrays is very useful when you have parallel outputs like our 4-bit timer does, because the output value can be set in one line of code, as you'll see in the architecture. Next, we'll build the architecture, which we'll name RTL. The signal called count will be used to hold the timer's current value. We'll use a process called timer 0 that has the master reset and clock in its sensitivity list. If reset is ever 1, then the count value should reset to all zeros. Notice that to assign a value to a standard logic vector, we use double quotation marks. Otherwise, else if clock is a rising edge, simply increment the signal count. Then end the if statement, end the process timer 0, and assign the 4-bit standard logic vector count signal to the 4-bit standard logic vector LED output, and end the architecture RTL. Go ahead and save the file as lesson6.vhd, and then start the compile process. After the compile is successful, pull up the pin planner and assign all of the pins in our port to where they should be connected. Then recompile the project, and again, double check that the fitter and our defined pin locations match, as they do. Next, we need to build up the hardware schematic to go with the custom timer we just designed in a CPLD. The power regulator circuit is a 9-volt battery that connects to an LM317 variable voltage regulator. 2 resistors set the output voltage of the LM317 to 3.3 volt, and then 2 10 microfarad bypass capacitors make sure the circuit will have enough current for continuous operation. A resistor and LED are added to the 3.3 volt output as a power good notification. For the CPLD connections, we have all of the VCC pins connecting to 3.3 volt power and all of the GND ground pins connecting to the circuit ground. Our master reset pin 44 connects straight to ground with a 10 kilo ohm pull-down resistor. Then we have our 4 resistors and 4 LEDs to display the current timer count value. These connect from pins 19 through pin 22 to the different LEDs and then directly to ground. The clock generation circuit is an ICM 7555 timer module that connects to 3.3 volt power and circuit ground. The clock output signal, pin 3, connects to the CPLD's global clock input at pin 37. Then we have two 10 kilo ohm resistors and a 10 microfarad capacitor which connects from 3.3 volt power to ground. And individually they connect to pins 6 and 7 of the ICM 7555. This completes the hardware schematic that we need to build, so now let's actually go build this thing. Here are all the parts that we'll be using in this experiment. The larger parts are a jumper wire kit, components kit, and a breadboard. The smaller parts from the components kit are a CPLD breakout board, an ICM 7555 timer module, LM317 voltage regulator, 3 10 microfarad capacitors, 5 470 ohm resistors, a 390 ohm resistor, a 240 ohm resistor, 3 10 kilo ohm resistors, 5 red LEDs, and a 9 volt battery connector. Now we'll use a step-by-step, part-by-part time lapse to show you how we built the circuit on our breadboard from beginning to end. First with the power regulation circuit, then the CPLD connections, and lastly the clock generation circuit. With the circuit built up, let's power it up, connect the JTAG programmer to the CPLD board, and the other end to our laptop computer. Then we load up lesson 6, and let's pull up the programmer tool. Add the .pof programming file, and then program the CPLD image for lesson 6. Right away, you can see the timers beginning to count. If we overlay the binary values above the LEDs and convert them from binary numbers into decimal numbers, it's very obvious that our 4-bit counter simply counts from 0 to 15 over and over and over and over. So hooray! Now we know how to keep track of timing using a clock input signal to our CPLD. You might be wondering, why is being able to keep track of timing so important? Well, the answer is quite simple. In digital electronics, we have to use timing to know when a logic 1 or logic 0 should be output. Otherwise, the output would not be valid and it would mess up the system. Like here, where we output digital signals to tell a motor how fast to spin, or here, where a CPLD outputs control signals to an LCD display, telling it which letters to display. As another example, each of these LEDs is being output a unique PWM signal to make each one have a unique brightness. On top of that, the brightness level between the LEDs is constantly changing to create a neat visual effect. This can only be achieved by keeping track of time to know which signals where should be outputting what value.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
Up to this point, everything we've done has been either a single logic block or a single process. In the next lesson, we'll build two hardware modules that operate independently of each other, but inside of the same CPLD.